All right, so we're going to keep looking at graphing sine and cosine. So we did all the shifts yesterday, left and right. We call that a phase shift. Up and down, vertical shift. And today we're going to look at some stretches, and we might get into the multi-step transformations. We'll see. So when we start stretching up and down, we're going to be changing the height. Well, the height of a graph is called the amplitude. And the amplitude is measured as a distance from the center of the graph to the peak, or you could measure from the center of the graph to the minimum. It would be symmetrical. That's the amplitude. But the amplitude is it's a measure of distance from the center line. Because it's measuring distance, what kind of number does it always have to be? Yep.
Positive.
It does have to be positive. Okay, so whenever I ask you for the amplitude of a function, you have to give me a positive number. All the amplitudes we've done so far for every graph have been 1. Even if you take a graph and you shift it up, say you had a graph shifted up like this, that graph still has an amplitude of 1. Its highest value might be like 5, but the amplitude is still 1, because if you draw in a center line and then you measure the distance from the center line to the peak, that's still 1 unit. Any question on the difference between the highest value that it hits versus its amplitude? Amplitude has been 1 up until today. It's going to change with the next couple problems we look at. So we're going to be stretching and compressing today. What kind of arithmetic is involved when you stretch or compress? Yeah?
Division and multiplication.
Right, we're looking at multiplication or multiplication by a fraction, like 1/3, 1/2, which is like division. But the point is, it's going to not be addition and subtraction. Okay, that's for shifting. If we're going to start out with a amplitude change, which is like a vertical stretch, okay, or compression, it's going to be multiplication. And where would it be if it's affecting the vertical? Would it be on the inside, or would it be on the outside? Think about where the vertical was yesterday. Yeah.
It would be on the outside.
It would be on the outside. So an amplitude change, or again, I can just put vertical stretch in parentheses, is when you multiply by a number on the outside. Just like that. C could be any value that you want, except 0. C can't be 0. And if I give you something like that, and I just say, what is the amplitude? You just take the absolute value of the number that's in the front. So what we're doing is stretching and compressing the graph along the y-axis. So let me show you on a graph what an amplitude change looks like. Here's sine, and I'm going to graph 3 sine. Okay, so what you're seeing in blue, that's just the original sine function. It goes from 1 to -1. 3 sine is going to be 3 times as tall. It's going to go from 3 to -3. Has it moved left and right? It's just been stretched vertically. That's an amplitude change. So, any questions what an amplitude change looks like? So that's a stretch. I could have also done a compression, which would have made it less tall. So we're going to start out with a few problems. We're not even going to sketch them. I'm just going to give you an equation, and I'm going to ask you what is the amplitude. So I'm looking for a number. And the way we find it is to take the absolute value of whatever number is in front. Let's try, well, kind of like the one I just graphed. I did sine, this is cosine. What would be the amplitude of 3 cosine x? Yep. 3. Yep.
That's it.
So you're telling me that if you put in the center line and you measure the distance that it goes off the center line, it goes 3 units above it and it goes 3 units below it. It's always symmetric. How about the amplitude of this one? 4/3 sine, that's a 4, x plus pi over 2 plus 6. Yeah? 4/3. There's some other transformations happening, but those don't have any effect on the amplitude. We're shifting it up and we're shifting it to the left. But that's not stretching. The only number that affects the amplitude is the 4/3. And how about this one? Y equals -2 sine x. What's going to be the amplitude of that one? Yeah, 2. I'm not saying the negative isn't going to do anything. The negative does do something, but it doesn't have an effect on the amplitude. What does the negative cause the graph to do? Yeah, flip. Yeah, the negative is, it's going to take a graph that looks like this, and instead it's going to make it look like that. It's going to flip it. But so we do have to use the negative when we do the sketch, but when I ask you for the amplitude, you just tell me 2.
Would it ever flip over the x-axis, or always the y?
So for a vertical, it would always flip over the x. When we get to multiplying by a number on the inside, that's when it could flip over the y. But we're not going to get into that. But that's when it would happen if you had a negative over there. Okay, so the next step is to find those 5 points that are going to make up our new chart. Which values are not affected by stretching up and down? Yeah. Yeah, x values are not going to be affected at all. Okay. All you're doing when you stretch is you're taking a point that was here and you're moving it up there. There's no left and right movement when you stretch up and down. Okay, so x's are going to stay the same. Whenever the x's stay the same, that's nice because the x's are the ones that are harder to work with. So for the next few problems we do, the x's are going to be 0, pi over 2, pi, 3 pi over 2, 2 pi. Okay, if the x's are going to stay the same, then we know the y's are going to change. All we have to do to find the new y values is to take the original y values and multiply them by c, whatever the number was in front. Notice I didn't say multiply by absolute value of c. You just use the number in front, whatever it is when you're doing the graph. If it's a negative, you need to use the negative because that causes it to flip. So just multiply all the old y values by whatever the number is in front. Don't do anything else to the number. Okay, taking the absolute value, that's only if I ask you about amplitude. Yeah, so taking the absolute value is only if I ask you a question, what is the amplitude? You don't want to give me a negative number there. Any question on that? So again, arithmetic, very easy. All you're going to have to do is take a 1, a -1, or a 0, and multiply it by a number. So this is the easier of the two transformations today. Right. Let's try 3 cosine x. Okay, what kind of arithmetic are we doing to the cosine function? Add, subtract, multiply, or divide. Yep. Yep, we are multiplying. And because we are multiplying, that makes it what kind of transformation? just in general. Yeah, makes it a stretch. Any multiplication is a stretch or compression. But specifically, we are multiplying on the outside. So that makes it a what kind of stretch? Yep.
Vertical.
Vertical. Yep. Because it's a vertical stretch, we just said all the x's stay the same. So let's write them down. What are my x's for cosine? Yep, Caleb.
Pi over 4. 0.
Yep.
Pi over 2. I think just pi.
Pi.
3 pi over 2. And 2 pi.
2 pi. Okay, so there's my original x's. Okay, I'm going to put my original y's off to the side. River, can you tell me my original y's
For cosine.
for cosine?
1, 0, negative 1, 0, 1.
Okay, so those are the originals. And Julia, what am I going to do to all 5 of those?
Multiply them by 3.
Yep, times them by 3. And Diego, when I multiply them all by 3, what are going to be my new y values?
The first one's going to be 3, the next one's going to be 0, that one's going to be -3, 0, 3.
There you go. So that's your table. And that's how you find the new y values when you do a vertical stretch or amplitude. You're changing the height, changing amplitude. Any question on the table? Now, a lot of my sketches are going to look the same today because when I change the height of something, if I changed it and made it like 20 times cosine x, I don't want to have to draw something 20 times as tall. So what I'm going to do is I'm going to scale my y-axis. Because I'm going to scale it and go by 3s, every graph I do today is not, it's going to look the same. Because I'm changing my scale, I'm not changing the size of the sketch. X's, we can just write those down. And now we'll plot our points. 3, 0, negative 3, 0, 3. 3, 3, 0, negative 3, 0, 3. And remember, that's part of a wave, so try to make it look like it's a wave. If I had to do the graph of 10 cosine x, the picture would look exactly the same. I would just change this to a negative 10 and a positive 10. That way I don't have to draw my graph 10 times as tall. Any question on that one? Okay, let's try another vertical type of transformation. What's going to happen this time that's a little bit different than last time? Besides the fact it's sine and not cosine, that's different. Yep.
Multiply by fraction.
Yep. So what's that really going to do?
Basically divide. It looks like it's going to.
It's going to compress, yes. So it's going to compress it. It might not look compressed depending on how I set up my scale. We'll see, but it is going to compress it. Yep. Okay. When we compress it vertically, which values stay the same? Yep. X's, okay? Those X's, hopefully you're starting to get those by now. 0, pi over 2 pi, 3 pi over 2, 2 pi. We use them a lot. Okay, off to the side, just to help me, I'll do my original y's. What are the original y values for the sine function? And remember, there's lots of original y values. We're just doing one cycle. Okay? If you can do one cycle, you can copy and paste it to do a second cycle. So what are the y values in the first cycle? Yeah.
0, 1, 0, negative 1, 0.
0, 1, 0, negative 1, 0. And we're going to take all those y values and do what to them? Yep.
Or
Can you
multiply
be
them
more
by
specific?
1/2.
Yeah, times them all by a half, or divide them by 2. So 0, half, 0, negative a half, 0. That's it. So that's a vertical transformation. In this case, it's a vertical compression. But I would still describe that if I had to write a sentence. I would say vertical stretch by 1/2, which really means compress. All right, I think I'm just going to leave my y values at -1 and 1. Because 1/2, I can go in between the lines pretty easily. And my x's. Okay, so this one will look compressed because I didn't change my scale. I am going to change the size of the picture, but when you change the picture and make it smaller, sometimes that's easier than having to make it huge. So it's going to take up less space. I'll just sketch it. So we go through the origin, up to a half, back to 0, negative a half, back to 0. That's the new graph. The original graph would have gone up to here and down to there. This has been compressed. Okay, any question on that one? All right, let's look at this one. Actually, let me ask the amplitude. What's the amplitude of example 2? Yep. Example 2.
Oh.
3, and then the amplitude of example 3. That's 1/2. What's the amplitude of example 4? Yeah, 1. There is no amplitude change. But that doesn't mean something isn't happening. Something is happening. What's happening? Yeah,
It's flipping.
it's flipping over which axis? Yeah, it's flipping over the x-axis. So there's no change to the x values. Those are staying the same. 0, pi over 2 pi, 3 pi over 2, and 2 pi. But what are all the y values going to get multiplied by, which won't change the amplitude, but it will flip everything over the x-axis? Yep.
-1.
Right. You're multiplying all the y values by -1. So we're still doing it like an amplitude change, even though it doesn't change the amplitude. Multiply everything by -1. That would be your new t. And I'm going to hold off on the sketch. Is there any question on how you would do the sketch? It's going to look just like the other graphs we've done, except it's flipped. So instead of the cosine being like the, more of like the valley, it's going to be more like a mountain because it's flipping. So that's pretty much it for the vertical stretch. And again, that's the easier one. So we've shifted up and down, shifted left and right, stretched up and down. What's the last thing we have left? Yep. Stretch or compress left and right. Okay. And that is called a period change. So stretch or compression. What we said, and we did this yesterday, what is the period of a sine or cosine function? How far do you have to travel along your graph before the values start repeating? It's basically right on the board right there. Yep.
2 pi.
Right, you have to travel a distance of 2 pi units from start to end, and after you've traveled that far, your graph is going to repeat itself. Well, that's been true for every transformation we've done, because we've never stretched or compressed the graph horizontally. So when we stretch or compress horizontally, we can take a graph that starts out looking like that and ends up looking like the one you're going to see in red in a second. So what I did with the red graph is I compressed it by a factor of 3. So now for every cycle that you were getting in blue, you're getting 3 cycles in red. I stretched it by 1/3. And what that means is because it's repeating faster, you don't have to travel as far before it starts over again. Okay? With the blue one, you've got to travel halfway across the screen. With the red one, you only have to travel a little bit, and then it's going to repeat. Okay. So 2 things we're going to do. First is we got to figure out how far do you have to travel before it repeats. What's the new length of the cycle? And then second, how do we graph it? Okay, with a table. So we just said that. And now we're changing that. Okay, this is stretching and compressing. So what kind of arithmetic do you think is going to be involved? Yep,
Multiplication.
it's multiplication. But where is it going to be if it's doing it horizontally? It's going to be multiplication, but it's going to be where? Yep,
Inside.
on the inside, okay, inside the parentheses. If you've been using the letters I've been using as you take the notes, you're automatically taking the notes for multi-step transformations as well. Because there's an order you have to do them when you start to have more than one in a problem. It's the same order we've been using all year. This transformation would be the second one. This transformation is the third one. That's why I used a C. Right? And then yesterday I used an A when we did phase shift, because that's the first one. And I used a D when we did vertical shift, because that is the last one. It's the same order we use all year. So earlier someone asked me about, well, what happens if we get the negative inside here? Yeah, I would flip over the y-axis, but we're just not going to do that. Okay, we're only going to look at examples where b is positive, so it will never flip over the y-axis. It's not hard, it's just we're not going to get into that. Okay, so period change, stretching and compressing horizontally along the x-axis. And if you make this a big number, okay, bigger than 1, 3, 5, 20, what does that do to the graph the bigger you make this number? Yeah?
Smaller, or the closer together?
Right, the more compressed it gets. Remember, this is backwards because it's horizontal. The bigger you make b, the more compressed it's going to get. The smaller you make b, like 1/3, 1/2, 0.2, things like that, numbers that are less than 1, that will cause it to stretch. So we're stretching and compressing horizontally. What values in the table are not affected by stretching and compressing horizontally? Yep.
Y values.
The y values. Unfortunately, the y values are easy to work with. We don't get to work with these. Okay. So all the y values are going to stay the same. So we are going to have to work with the x values. And I'll show you how to do that in a little bit. What's the normal length again of the period, if you don't stretch or compress it. Yeah.
2 pi.
Right, starts at 0, ends at 2 pi. If you've got a graph that does something like that, you compressed it. What I want to figure out now is what is the new length from start to finish. And the way you figure that out is with this formula. You take the original period, which is 2 pi, and you divide it by b. And what's b? B is whatever number is in front of x. Okay, so I'm not saying the period is b. I'm saying it's 2 pi divided by b. So let's try a couple examples where we don't even sketch. We just find the length of the period. So think of a 2 right there. Should the 2 cause the graph to stretch or compress? Which one? Yep.
Compress.
It should compress. That means the length of the period should get smaller. So we started with 2 pi. This should be less than that because we're compressing it. Okay, what's b in example 5a? What's the b value? Yeah, 2. So you're going to take 2 and you're going to fill it in right there. So you have 2 pi over b, which in this case is 2 pi over 2. And what is 2 pi over 2 reduced to? Pi. That is the new length, pi. How does pi compare to 2 pi? Yeah,
It's half.
it's half of it, yeah. And that's exactly what putting a 2 here does. It stretches the graph by 1/2. So technically it compresses it by 2. And that's what the cycle did. It compressed, it got half as big. Let's try this one. Cosine 1/3 x. Okay, what should happen here? This time the b value is a 1/3, so the graph should do what? Yep. Yeah, it should get bigger. So we're starting with a cycle of 2 pi. We should be getting something bigger than 2 pi when we're done. What's going to be the calculation? You don't have to give me the final answer. Just tell me what's the formula that I'm going to use to find the period. Yeah?
Is it 2 pi over 1/3?
2 pi over 1/3. How do you divide 2 pi by 1/3? Yeah.
You have like, actually,
Yep, those.
The same as like multiplying it by 3.
Right. Instead of dividing by 1/3, you're going to multiply it by 3. That's what dividing by 1/3 does. You flip it and multiply it. And what's 2 pi times 3? Yep.
6 pi?
6 pi. Is 6 pi bigger than 2 pi?
Yes.
Yeah. So it's 3 times as big. That means you need to travel 3 times as far before the graph repeats that because it's stretched out. All right, and let's try this one. What's going to be the period in this case? Yep.
pi.
Pi. Well, b is pi. But what's the, can you plug that into the whole formula?
It'd be 2 pi over pi.
2 pi over pi.
So would it just be 2?
2. Yep. So that means this graph would have a cycle from 0 to 2. This would be the first time we've ever seen a graph that would have nice labels on the x-axis. The labels would not have pi in it because the pi canceled. So you might have labels of like 0, 1, 2, 3, 4. You would have nice labels this time. Okay, and let's see, I got one more. Okay, lots of different numbers in that one. But what's the number that you're focusing on to find the period? Yep,
3.
the 3. Stretching vertically by a factor of 2 and shifting up 2 has nothing to do with stretching and compressing. Every transformation is separate. What's going to be the period of this one? 2 pi over 3. Yep. Okay, so any question on finding period length using that formula? Now I put it only works for sine and cosine. Technically it also works for secant and cosecant. We haven't done that yet, but if I gave you a problem like this and said find the period, you'd do exactly the same thing that you did in example 5. So it does work for secant and cosecant. It does not work for tangent and cotangent. That's different. But that's not for today. All right, so we already said that the y values are staying the same, so we don't get to work with those. That means the x's are going to change. And the way we're going to find the new x's is we're going to take the old x's and divide them by b. It's kind of like what you did right here. Divided by b, except you're not just going to do it one time. You're going to do it 5 times. You're going to do every x value divided by b. Now, do you really have to do it 5 times? No, because you're going to see a pattern eventually. And once you see the pattern, we can go with that. So let's try a couple examples of period change, and I think. And then maybe we'll look at a multi-step, I'm not sure. Okay, so first one is sine 1/2 x. I'm going to do my table over here just because I have more space. What is staying the same?
Y.
Y. And what are my y values for sine? Make sure you look at sine, don't look at cosine.
0, 1, 0, negative 1, 0.
Yep. 0, 1, 0, negative 1, 0. Okay. I still need the original x's. I'm just going to put them on the outside. What are the original x's for sine? Yep.
0, pi over 2, pi, 3 pi over 2.
Okay. So those are the originals. And what am I going to do to all the original x values? Yeah. Wait, you're going to take all the original x values and divide them by 1/2. Now, 1/2 is a fraction, so dividing by a fraction, that can be kind of confusing. Dividing by a half is the same as multiplying by what? 2. So I'm going to multiply these all by 2. So I'm going to get 0. What's pi over 2 times 2? Pi. And then pi times 2? 2 pi. And the next one? 3 pi. And the last one? 4 pi. So when you multiply them all by 2, that's your new table. And those will be your labels on the x-axis. So this graph has stretched out twice as long as it normally would be. But it's not going to look twice as long because I'm going to change my scale. If I don't change my scale and I stretch something like 10 times as big, problem is I'm going to run out of room to draw it. So I'm going to make this 0. This would normally be pi over 2, pi, 3 pi over 2, and 2 pi. I'm going to label them like this. Now, because I changed my labels, I don't have to worry about drawing it huge. Okay, so start at the origin. 1, 0, -1, back to 0. And that's your sketch. Okay. Any question on the table or the sketch? All right, so that one was a stretch. Let's try one that's a compression. Okay, cosine 2x. First thing to look at is what kind of arithmetic is it? It's multiplication. It's a stretch. And it's next to the x. Next to the x means it's inside. Okay, so that means y values stay the same. What are my y values for cosine? Yep.
1, 0, -1, 0.
Say it again. 1, 0.
-1, 0, 1.
Yep. Okay, original x's, I'm going to put those on the outside. And what am I going to do to all my original x values to get the new ones? Yeah.
Divide by 2.
Yeah, I'm going to divide them by 2. And dividing by 2 is the same as what? Yeah. Yeah, just taking half of all of them. Yeah. So either divide by 2 or just take half of everything. Well, half of 0 is 0. What's half of pi over 2? Yep. Pi over 4. What's half of pi?
Pi over 2.
Pi over 2. And it doesn't look like a pattern, but if you wrote everything with a denominator of 4, that's 0 pi over 4, 1 pi over 4, 2 pi over 4. What's this one going to be? 3 pi over 4, and 4 pi over 4, which is just pi. Okay. Any question on that one? Let's make our our graph. So 0, 1, -1. Start at 0. And these are all going to be labeled using the labels in the x column. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. But I reduce them because we're supposed to reduce if you can. Okay, so 1, 0, -1, 0, back to 1. Again, the graph doesn't look like it's been stretched or compressed in any way because I changed my scale. Any questions on that one? Let's do one more, but I'm not going to graph it. We're just going to do just the table. All right. Can somebody kind of guide me through it? What do I do first?
Put the original cosine y's down.
Okay. And what are those?
1, 0, -1, 0, 1.
Somebody else tell me, what do I do next? Yes.
On this side, write down all your original x's.
Okay, let's put the original x's. Can you tell me those?
0, pi over 2, pi, 3 pi, over 2, 2, and then, yeah, 2.
Okay, so I got all my original x's. Now I gotta find the new ones. How am I gonna do that?
Divide by pi over 3.
Okay, you could divide everything by pi over 3. Or
Multiply by what?
multiply by what?
3 pi?
3 over
3 over pi?
3 over pi. Multiply everything by 3 over pi.
cancels out all the pi.
Yeah, it's gonna end up canceling out all the pi's. First one, it's just 0. But the second one, 3 over 2, which is
1 and a half.
1 and a half.
6.
Next one, 3. And the next one,
3, 4.5.
4.5. And the last one, 6. It's going up by 1 and a half each time, and the pattern I think is easier to see because there's no pi in it because it canceled out. So when you first look at it, you might think that's a pretty awful number to have in front of x. Like it's going to make the numbers really hard. It actually doesn't. It makes the table very nice. And you wouldn't need any labels if you didn't want to put them here because you could go by 1s on the x, 1s on the y. Because you only have to go out to 6 and you only have to go to 1 and -1. Any questions on that? All right. All right, so last thing we're going to look at, now that we've done all the individual transformations, is a problem like that. It's multi-step. So it's got horizontal shift and a vertical stretch. If you know how to do each transformation individually, then doing them together like that is exactly the same. You just have to remember that there is a certain order that you need to follow. And just in case we don't remember which ones are which, phase shift, that's the horizontal shift. Period change is the horizontal stretch. Vertical stretch and vertical shift. And if you look back at the notes as we were going through it, I used the letters A, B, C, and D. So if I put it all together in one function, it would look something like this. A is your phase shift. B, that's your period change. C in the equation below is the vertical stretch. And D, that's the vertical shift. Any question on that order? If you don't follow that order, it's like not following PEMDAS. So you'll get a different answer some of the time. But I would not try to guess when you can and when you can't follow that order. I would just follow that order all the time. All right, so let's look at this one. How many transformations does this one have out of the 4? It has 2. Yep. What's the pi over 2?
Phase shift.
Yep, that's a phase shift, so we got 1. And what's the 2 in front?
Stretch.
Vertical stretch. So we have 2 transformations, and one of them is going to do something left and right. One of them is going to do something up and down. So technically the order doesn't matter because they are on separate axes. They don't interfere. When the order really starts to matter is if you do two transformations on the same axis, like a vertical stretch and a vertical shift at the same time. But again, just stick with that order. Okay, so based on the order, which one should we do first? Yep,
The phase shift.
the phase shift. So I'm going to put all my originals, I'll do my work over here. The phase shift is going to move it left and right. Are we going to add or are we going to subtract to all the original x values? Yeah,
Subtract.
we're going to subtract. So this is what we did yesterday. And how much are we going to subtract? Pi over 2. So in this problem, there is no copying the original values because the original values are not going to be in the final answer. Everything is changing. All the x's, all the y's. Okay. Can anyone tell me what we get for my new x's when I do all those calculations? I just did them over there because I didn't have enough space. Yep.
Negative pi over 2, 0, pi over 2, pi, 3 pi over
2 pi.
3 pi over 2.
Yep. So it's negative pi over 2, 0, pi over 2, pi, 3 pi over 2. Yep. Now, the original y values for sine, 0, 1, 0, negative 1, 0. Those aren't staying either. What are we going to do to all of those? No, we're not going to divide them by 2. You do something with the 2, but we don't divide them by 2. Yeah.
Multiply.
Right. So you don't want to do anything backwards on the vertical stuff. Okay, so we're going to multiply them all by 2. So 0, 2, 0, negative 2, 0. And that's it. That's a multi-step transformation. So you just did 2 at the same time. Okay, so for the sketch, labels, you need 1 in the negative, and then everything else is 0 and up. So let's put negative pi over 2, 0, pi over 2, pi, 3 pi over 2. Now, y's, I got to go up to 2 and negative 2, so I'm going to scale it. If I don't have enough space. And now graphic ones. So negative pi over 2, 0. 0, 2. Remember, that's 2 because I scaled it. 0. And those are your points. Any question on that one? So there's a few more multi-step ones we'll do. They're not any harder, but we'll do them tomorrow. Okay. So that sets us up pretty good to finish 6.3 easily because I normally do all this in one day, and we already did 10 minutes of 6.3 today, part 3. Let me see. Period. Just hold on one second.
You're good.
Let's do.
I can see.
Okay, so number 9, that's a multi-step.
Oh.
Okay, so there's 9 9 questions. Okay, for each question, make sure that you show the table and you show the graph. That wasn't a problem last night. I think everybody had both. Make sure you do the same thing this time.